Yo, what's up, everyone? Here we are, the last lesson of the semester. Woo, nope, a week nine. Crap. I forgot to change the header. It's all good. I'll change it for you guys. But yeah, problem set two, week nine. And I think it's going to be a decently quick lesson because I'm going to talk about essentially continuing what we did in the last lesson, which is expected value. And then we're also going to talk about standard deviation again. And yeah, I just didn't pace the first lesson perfectly. I think if I did everything, it would have been like a 30-minute lesson. So might as well have two kind of shorter lessons. And also like I really love the logic for this, the explanation for this. And while I was teaching last time, I forgot how I like to explain it. So I did my studying, I did my research, and I think I got a cool lesson. But anyway, first we're going to start with an example that was the end of the last lesson. And it just says, imagine you go to the arcade and play the game skee ball. Based on the location and size of each of the holes, you create the following probability distribution, showing the likelihood you score each of the scores below. So hopefully you guys have played skee ball before. It's pretty fun. And when you throw the ball, right, there's different holes that you can land in, and they give you different points, right? So a probability distribution was created to estimate how many points you're going to score every time you throw the ball up into the skee ball. So that's the setup for this, and hopefully that makes sense. If you see this 10 and then 0.3, that means there's a 30% chance that they score 10 points. And then you move all the way, and then the highest one, the 100s, had a 10% chance of scoring. So I drew this for us before we started because this is not even like new material. We've drawn a lot of distributions before. And if we're looking at this, we could even describe it as like being skewed right, right? Most of the outcomes are 10 and 20 and 30, but then the 40, 50, and 100 are skewing us to the right. And before we do the next part, just remember that if you have a discrete random probability or random variable, you have to put the numbers below and not in between, because this 30% is the value 10. It's not in between 10 and 20. Okay, so that's really important. And then the other thing to think about is just that if we're going to talk about the center of this, the mean of the distribution, it's going to be pushed to the right by these skewed right points. Before we talk about the formula that we already did, we're going to talk about how we can get there. So before we overthink anything, we're going to do B, and it says, if you throw the ball 10 times, what is the probability? Sorry. If you throw the ball 10 times, what would you expect your total score to be? And if you want to pause and think about it, that's good too. But we know that what this distribution tells us is what happens if we throw the ball a single time, right? So if we throw the ball a single time, there's like a 30% chance it's 10. That's the most likely outcome. But how can we apply that to if we throw the ball 10 times? So let's just start with this 100, right? The hundreds are the hardest place to get. And it says that we have a 10% chance or a 1 in 10 chance, right? And I'm just going to write that out. 1 in 10, we get 100. So if 1 out of every 10 throws is 100, and it asks us what our expected score is if you throw the ball 10 times, just think that we expect the ball to be 100 one time, right? We expect the ball to be 50 one time, and we expect the ball to be 40 one time. If we throw it 10 times, and each of these has a 1 in 10 chance of occurring, think that each of them we can expect to happen a single time. Does that make sense? So on the bottom here, we're just gonna like predict what those 10 throws would be in the most normal situation. So if there's a 30% chance it's 10, that means that we would expect the throw to be 10 how many times out of 10? 3 times, right? So let me just show you, this one works really well in this case. But if we throw it 10 times, we expect this 3 times, this 2 times, this 2 times, and these 3 one time. And if I add that up, that's going to give me a total score, right? 10 plus 10 plus 10. I hope that makes sense to everyone. What happens if we throw the ball 10 times? What do we expect to happen? This is the outcome we expect. These 3 outcomes happen the least, so we only add them once. but these outcomes happen twice as much, and this outcome happens 3 times as much. So we would expect a score of 320. I hope that makes sense so far. For C, it says based on the answer above, how much would you expect to score per turn? Okay, so this is where we're going to start to get to the actual formula for this. But our expected roll is 320 if we throw the ball 10 times, right? So we throw it 10 times and we'd expect our total score to be 320. So if we know that out of 10 times or in 10 times, we expect 320, how much do we expect in a single turn? That would just be 320 divided by 10, right? And I hope people see this logic because I still think I'm not explaining it perfectly. But think that the average or expected per turn is 32 if you expect to get 320 in 10 rolls, right? So on average, you expect to get 32, okay? And that is the expected value, okay? So that's what we're always going to be solving for. What do we expect to happen in a single run of this event? What is expected of us? And we just found that in a single turn, it's 32, okay? So we want to talk about how we can get that kind of using this logic. Okay, so we want to find derive this formula for the expected value. So I'm going to start by putting in my values and we'll go from there. So what I want you to think is that when you find the mean of anything, you take all of your values, you add them up and you divide by a number, right? That's kind of what we were just doing. But if we want to find this formula for a single value, all you're going to do is you're going to take every single possibility and multiply it by its probability, okay? And what that does is instead of predicting what happens in 10 rolls, right? It's just going to predict what happens in a single roll, okay? So let's do it. I think my explanation was kind of crap. I'm a little disappointed in myself, but it's fine. I think it's like I'm getting there. I think I'm explaining it well enough that you guys can make the leap. But if you do this, you're weighting each number by its percent, which is a really easy formula to do. You're gonna get the same value of 32, okay? And think that what you're doing is you're trying to find the center of the distribution, of the probability distribution. And if you were to guess just from this, you know it's not gonna be that close to where most of the data is. It's gonna be pushed to the right, and that's where 32 is, okay? So think of the expected value as like the weighted average, and you take every value and multiply it by its percent. Because these probabilities don't happen that often, they get multiplied by a small number. But these probabilities happen way more often, so this gets multiplied by the highest coefficient. So that's my explanation for expected value. Hopefully that's fine. And in practice, that's pretty easy. But now we're just going to talk about what's a little bit tedious, and which is the standard deviation. And remember that we can talk about what's the average roll or the average score, but we want to know how much that spreads from the center. So all you're going to do is something that we used to do for standard deviation. You're going to take every value and subtract away the mean and then square it. Hopefully you guys remember that. Remember for the initial standard deviation for like just for data, you would do this and then add them all up and divide. But now we're going to do this and multiply it by the percent. Okay, so this is just kind of something to memorize. But instead of doing a weighted average to figure out the middle, we're going to do a weighted standard deviation. Okay, so this tells us how far away this data point is. This 10 is from the center. And this weights it because this is a lot of our data. So that's how that standard deviation formula works. If you've been good with standard deviation in the past, hopefully that makes sense. Take each point, figure out how far away it is from the center, square it so all numbers are positive, and then weight it by that probability. So I'm just gonna fast forward. Okay, So I got a really clean answer, 676. It could be wrong. I mean, that was kind of tedious, but I would recommend doing it in the calculator just so that you can see if you have the calculator skills to get the right answer. So first, that's going to be the variance. And this is like the last part of this lesson, pretty much done. We're just going to review. But as always, when you put a formula in for the standard deviation, it solves for variance, but then we just take the square root of that to find the standard deviation. Okay, so I'm going a little quick, but this isn't like the most important concept. Wow, and it became exactly 26. Like that's remarkable for random numbers. But these are just the skills that we have to remember for the whole year. Okay, so we found the variance. It says that we vary this much, but to weight it or like bring it down to a number that's like related to our question, we take the square root and that gives us standard deviation. So standard deviation says that on average, a roll is 26 away from the center of 32. Again, it's totally cool if you didn't understand all of that. And really the only takeaway you need is to use these formulas to find expected value and standard deviation. All right, excellent. Let's tackle this second question and then also like look formulas on the bottom. Okay, good. So this question says you love going through the Starbucks drive-thru on your way to school. The following probability distribution shows how many cars you can expect to be in front of you if you get there at 7:30. So I'm going to fast forward and draw it, but we know that these are the number of cars and these are their probabilities, right? So when we have to find the expected value, it's actually so easy. We did a lot of talking, but all we're going to have to do for this is multiply 0 to 0.1 plus 1 times 0.2, etc. But first, let's just draw the probability distribution. Okay, so that's what the distribution would look like. These are cars on the bottom. And hopefully you're seeing that this is super similar to the stuff we did in the beginning of the year. And now we want to find the center number of cars. So the expected value usually makes a lot of sense in the context of the question. In this case, all it means is every time you go to the drive-thru, how many cars do you expect to be in front of you? So you take every possible value and you multiply it to its probability. Think of it like a weighted average. And if you do this, it's going to say where is the center of that distribution. If a lot of the data is in the middle, this data is pushing us this way, this data is pushing us this way, it's going to be probably close to where most of the percentages are. And I'm getting 2.15. And what's awesome about stats compared to other math classes is your answer is usually going to make logical sense, right? So if we saw that this is our distribution, it makes a lot of sense to say that 2.1 cars are expected to be in front of you every time you go into the drive-thru. So that's great. And then this sucks, the variance. But I like doing it again because it's good to just kind of remember what standard deviation is all about. You're just going to take every percent and multiply it by the distance that point is from the center, right? 0 is 2.15 away, and we weight it by 0.1. So we do that for every single point. I got the variance to be 1.5275. I really hope that's right because this stuff's difficult. And then the standard deviation is just going to be the square root of that number. Which is 1.23. That all sounds good and well to me. That sounds like a reasonable value. The standard deviation always has to be pretty close to your numbers itself, right? In my head, it makes a lot of sense to say that the average number of cars varies by 1.23 cars. right? A lot of the data is kind of close to 2.1, like within that range. All right, we're pretty much done. All I wanted to do for E was show you that things do circle. What E says is what is the probability that more than 3 people are in front of you? And we've done this exact kind of question before with this exact kind of graph. So you just have to be ready to do all kinds of things at once. And this is really easy. So if it's asking for a probability, that's going to involve adding up possible values, right? More than 3 cars in front of you. Think that this is this plus this, or 10% of the time, okay? So I did that really quick, but I'm going to give you some questions like that just to keep you a little bit on your toes. But yeah, that's a wrap for semester 1 of this class. Woo.